The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Welcome to the Department of Energy Zero Energy Ready Home Technical Training Webinar Series. We're really excited that you can join us today for the session on low-load, high-performance HVAC presented by Duncan Prawl with Ibicus. Today's session is one in a continuing series of technical training webinars to support our partners in designing and building zero energy ready homes. My name is Lindsay Parker. I'm the coordination support for the Zero Energy Ready Home program, and I'll be covering some general points on webinar housekeeping. Just so you know, all attendees will be in listen-only mode, but you can feel free to ask any questions you have during the session by typing them into, the GoToWebinar questions section in the application. We will be monitoring questions throughout the session, so feel free to type them in whenever you feel like it. And near the end of the webinar, we'll cover as many questions as we can. Also, this session is being recorded and will be placed on the Zero Energy Ready Home Resources website. Additionally, after the webinar, we will send around a PDF of the presentation to all of the attendees who have registered, and as well as any additional information on upcoming webinars. So now I'm going to hand it over to Jamie Lyons, who is the Technical Director of the DOE Zero Energy Ready Home Program, and he's with Newport Partners. And take it away, Jamie.
Okay, thanks, Lindsay. Welcome, everybody. Thanks for joining us. I'm just going to give a few words to sort of set the stage for Duncan Prawl and his presentation on low-load HVAC. You probably heard Lindsay mention a few times the program name of DOE Zero Energy Ready Home. That might sound a little bit new to some of you. Just within the last several weeks, DOE has formally started the process of changing the program name. It had been DOE's Challenge Home program, and now it's migrating over to what DOE feels and our builders certainly feel is a much more compelling name that communicates more of the value and what's different, what's special about these homes. So that's DOE Zero Energy Ready Home. For the most part, the program name change is really the only change that's taking place at this point. The specs remain pretty much the same as they were under the old name. The name change is really driven by some of our really strongest builder partners just simply requesting, when DOE went out for feedback, how's the program working for them? Do they have questions, clarifications, challenges, things of that nature? Very loudly and clearly, they requested a more compelling name, and so that's how we've arrived at the DOE Zero Energy Ready Home program name at this point. So we do want to work with our partners and make the program as successful as possible for them in building, designing, marketing, selling zero energy ready homes. So then moving on, just a few quick words about today's webinar. Myself and Sam Rashkin have the opportunity to go around the country with different training partners of ours, and we run 3-4 hour training sessions on all the sort of workings of the DOE Zero Energy Ready Home program. It's the business case, the value proposition, what are the market realities sort of driving the home building business towards this zero energy space. So those are great trainings, but in the context of those, and maybe you've sat in on some of them, the time is a little bit limiting. We don't have time to spend 45 minutes or an hour on a particular technical topic. So that's the genesis for running these webinars, where we can do more of a deep dive, 200, 300 level type of content on something like low-load HVAC. So that brings us here today, and we're running an entire series of these technical training webinars, which you can attend live or go back and look at the recorded webinar on the DOE site. That brings us here today to this topic of low-load HVAC. We hear a lot about this during our discussions with builder partners and raters. We hear it in the live trainings that we do, that what are good practices, what are the bugaboos we have to watch out for in HVAC design when our homes have just a fraction, maybe it's half the design load of homes that might have been built just 10 years ago. So we have much lower load that has implications on the equipment. That certainly has implications on the amount of air that's being moved around a home to meet loads. And it has implications on the design of that air distribution system. So Duncan Prahl, our presenter today, is going to sort of touch on those topics and share with you the best practices and some of the findings of recent research that he's been part of. Duncan is with Ibicus. He's a senior building performance specialist with Ibicus. And in that role, he has more than a decade of experience working with builders and developers to implement high-performance housing solutions using the DOE Building America research results. Duncan's projects have dealt with zero-energy homes, retrofit strategies, business processes for high-performance homes, and quality management programs for production home builders. Duncan also plays a strategic role with the Building America program. He's presented at numerous residential home building conferences and also conducts training for builders, designers, and trades. And lastly, Duncan is a registered architect in New York and earned a Bachelor of Architecture degree from Rhode Island School of Design. So with that, I'll turn it over to Duncan. If we want to let him start sharing his slides, he can jump in.
Sounds good. Thank you, Jamie. And thank you, Lindsay. I'm happy to be here today and share, in part, what wisdom we've found in working with builders in the low-load HVAC arena in a variety of different climates, and happy to field questions. I talked to Jamie earlier, and I said if there's anything I present that's unclear as I'm presenting it, if people have questions on it, feel free to jump in. So Jamie may interrupt me at times, but with that, I'll just start plowing forward. We are looking at what is the impact of the advanced enclosure having on the HVAC system and system design, and this is a challenge that we're experiencing in our consulting work outside of Building America, working with builders who are implementing Energy Star version 3 and having comfort complaints. And it really goes beyond the minimums of what Challenge Home or Energy Star version 3 are requiring, which is the biggest challenge, I think, is not just sizing the equipment right, putting the ducts in that match the airflows, and then maybe selecting a register to deliver that, but really, I think, rethinking the entire way the system kind of works. We've seen, as Jamie mentioned, a variety of different impacts that these lower load homes have in terms of the reducing heating and cooling loads. Also in southern climates, we're seeing, especially with the introduction of ventilation, a different latent to sensible load ratio and in different time periods over the course of the year. And as we're seeing right sizing being strongly sort of enforced and implemented both in the zero energy home, ZERH program and even in codes, this is a topic area that I think hasn't really caught up with the industry. I kind of facetiously say if you have problems with your HVAC system in your low-load home, the first two are kind of your options, which is try to go back in time when it didn't matter, figure out somebody else to blame it on, which is a bad approach in my mind, but typically what might happen. And really the top three solutions are down there below it. It's really understanding and thinking about what the space conditioning system is designed to do and how it's installed, and following the recommended guidance in ACA manuals J, S, T, and D. And manual T is a very important manual. It is not something, it's more of a guidance document than it is an actual design manual, but it has very good information about how air moves in the room that you're trying to condition. And if you take three things away from this today, I would say It's keep velocity up and mix and mix. And if you want to take 4 away, mix again. Those are the things that are really impacting comfort in these buildings, much more so than we have seen in historical types of systems. And as I mentioned, the energy efficiency of the house doesn't necessarily equal comfort. We've heard a lot of the value proposition is, well, you build this better enclosure and it's more comfortable for the occupant. Yes, in some respects, in that you have a better enclosure, you've got fewer drafts, but there are differing impacts of solar gains on different rooms that may not be inherently connected or near a thermostat that might overheat at certain periods of the time. And our experience in the real world is that comfort is the big driver for customer complaints, not high energy bills in lower load homes, and that if we don't get the comfort right, we're not really going to be where we want to be. So the types of discomfort problems that we have, and I could probably do a half hour on just what comfort is in general, but typically the problems that we experience is stratification, where the floor is cooler, the head is hotter, or the second floor is warmer than the first floor. Those are all issues of stratification, where the denser, cooler air has a tendency to fall and drop to the bottom, and the warmer, lighter air has a tendency to move up to the top of the building or the top of the space. The other main discomfort problem we can see is air blowing on people. Sometimes this is beneficial, especially in the cooling mode. This can be a useful tool, but typically with the air delivery temperatures that you're doing with a air conditioning system at 55, 58, 60 degrees, that air feels unpleasantly cool on people as a draft, and similarly, if they're feeling that draft in the heating mode, they may feel it as a cooling effect on their skin and not be comfortable. The hot or cold surfaces has really been kind of solved, I think, with the enclosure and the air tightness that we're getting in these buildings. It really has to do with what they call the mean radiant temperature, which is the surface temperature of all the objects that your body experiences. And with low E windows, with higher levels of insulation, we found that pretty much the mean radiant temperature in a building is tracks pretty closely within maybe one half to 1 degree of the actual air temperature in the building. So mean radiant temperature can be a big issue in very poorly built houses with bad windows, single pane or double pane windows, non-low E. But as you get up to the enclosure levels that we've got in these houses now, that's not really that much of a problem. And the last one is just the room-to-room variation in temperatures. ACA Manual J and D both give a guidance of plus or minus 2 degrees in the heating season and plus or minus 3 degrees in the cooling season. As a room-to-room temperature variation, an acceptable range of temperature variation. And to the best of our knowledge, we could track that down to the 1930s and 40s when some test houses were being built and measured in Illinois. And they determined that with these new forced air heating systems and an appropriately designed duct system, that roughly 2 to 3 degrees was about as good as you could get in terms of maintaining temperature differentials. So I don't know that this is necessarily tied to any real occupant response or desire, and more of a historical finding of how closely the room-to-room temperature differences can be maintained. We're doing actually some studying right now to look at large-scale temperature variation in a larger number of homes. Hope to have some better documentation and data in the upcoming future as to how buildings are really responding in that. So with HVAC, it isn't, to get this to work well, you really have to get inserted into the design phase. I tell builders and designers and HVAC contractors that to make the HVAC system work, you have to put it in the design program for the architect the same way you would say, I need a refrigerator in the kitchen, or I need a half bath in the first floor, or I need a closet off the foyer to hang my coats in. You need a space and a strategy for an HVAC system that the architects can use in the building and integrate into the design as they're designing the building. That impacts structural and impacts plumbing, but if you do that, you have a much higher level of, a higher chance of success to make the system actually work well. And this is especially important when we're trying to get all of the ducts inside the conditioned space, making sure we can run the ducts where they need to and integrate with the structure is really critical. So what we recommend, and this is probably, it's a difficult map to read, but if you blow it up on the PDF, this is essentially a flow chart of the design process going through schematic design, design development, construction documentation, and really these are feedback loops at each stage in the process that come from a variety of different people. So while the spatial massing and layout is important, you also want to have a schematic HVAC design as or strategy as you're starting to do your schematic design. You want to make sure you have a structural system that will work with the HVAC. You may want to do preliminary energy evaluation to give you a rough idea of how big the system might need to be and how big these ducts are and how many supply outlets you might need in a very schematic way early on. And then continually through the design process, making sure that those are checked, double-checked, and that they're as important as making sure that, yes, the refrigerator and the stove are in the right place in the kitchen, or that coat closet is appropriately located right next to where people are going to be coming into and out of the building. So a good forced air system really is to maintain the comfort in the house. It delivers and removes energy from the space. It makes sure the room air is mixed. It can help to maintain fresh air uniformity throughout the house, and if integrated with a ventilation system or ventilation strategy, you can certainly maintain humidity levels with them. More and more systems are having more and more humidity control, especially these smaller mini-split systems, but there may be in southern climates a need for specific dehumidification, which should be considered as part of the forced air system to maintain that humidity control. And ideally, you don't want the occupants to know it's there, and you just want it to operate efficiently. So to the point of where have we been and where are we going in terms of sizing, these are some numbers that we've pulled off of different housing projects that we've used over time, and you're really seeing that as we move up in energy performance up to the passive house level, we're getting system sizes that are really very small, going from the old 400 square feet per ton rule of thumb up through a 3,200 square foot house that might need a ton to a ton, not even a ton of cooling, depending on its size. And so we're seeing that becoming prevalent. With that, the important thing that we've seen is that the airflow that is being blown around the house is also undergoing a dramatic reduction. So where we used to have a lot of airflow with these larger systems, we don't have as much air moving through the building and around the building, which is a primary driver of maintaining comfort. So we've got less air volume. We have the same size houses. We have the duct lengths may be similar. To make sure that we get the airflow that we want, duct tightness is critical. So we may be air sealing ducts inside conditioned space, not for an energy purpose, but simply to make sure that we've got the air that we want to be delivered to each room in that room. So duct tightness becomes something important, but not necessarily from an energy standpoint. And there's also some selection considerations that you might want to think about with sheet metal versus flex duct and duct board systems, or a combination of duct board and sheet metal runouts. But with lower airflows and less airflow, the temperature rise at the longest outlet for short cycles may not get the air temperature that you want delivered to that room, and may drive actually temperature imbalances not because you don't have the right amount of airflow, but if the system doesn't run long enough, the temperature of the air leaving that longest run may be significantly lower than the temperature at the shortest run. And what we found historically is the shortest run is usually the one closest to the thermostat. So you may be starving the system, and I've got some information on that there. To help on this, we've come up with a few design guides on HVAC systems, not trying to supplant or replace the ACA manuals, but to help give some insight into what can happen when you do them right or wrong and how to more appropriately use them. And we went through one to kind of look at how do we, how can right sizing be manipulated in a way that appears to be right sizing, but really is giving the answer that the HVAC contractor wants. So we've done these three guides. There's the first one, which is the accurate heating and cooling load calculations. All of these can be found on the Building America Publications website. If you search for Building America Publications, it'll give you a link there, and if you just search Ibicus HVAC, each of these guides would come up as a strategy guideline. But we've done one for load calculations, we've done one for equipment sizing, and one for air distribution and sort of compact duct systems for lower load homes. And the important thing to recognize here is that this is really an iterative process, that we frequently, when we design duct systems and total HVAC systems, we may go through and pick one piece of equipment, design a duct system for that, find out that the blower really won't work, and may have to go back and find another piece of equipment that gives us the blower performance we need for the ducting we need. The benefit of compact ducts and short duct systems is that you can have a better range of performance with a specific piece of HVAC equipment, and you're not trying to tax getting long runs around the building. So this was the first guide. One, we demonstrate we can get, how can you manipulate loads to get something that looks right size but really doesn't. We exaggerated all these different items and came up with, in an Orlando, Florida, this house might have needed a 20,000 BTU cooling load, which might have ended up being a 2-ton air conditioning system with a 40,000 BTU furnace on it. Well, we can tweak these things and get that load up to almost 3 tons without a real problem. And it still looks like you've done them correctly. Same thing in Illinois. We went from a 40,000 BTU furnace to probably a 70 or 80,000 BTU furnace, and from a 2-ton air conditioner to almost a 4-ton air conditioner, 3.5-ton air conditioner. So when right sizing, it's very important to make sure you're not just seeing that the load calcs have been done, but they're using the appropriate indoor and outdoor temperatures, they're using appropriate infiltration rates, they're not derating the insulation or derating the thermal enclosure characteristics compared to how you've been doing that. We also went through, this is a couple of examples of houses that we've done which are, I would say, above what the ZERH requirements might be now, but are representative of what we see as some pretty high performance homes, both in Georgia and in Denver. And one of the things that is of interest to us is, while ACA and Manual J is calculating the peak load, that's the 1 hour that it's the coldest day, that really you're going to be taxing the system and hopefully having it run 100% of the time. But what's important to know is that you're also going to be running that system a long time in the intermediate shoulders between when it's at peak and at ambient, at sort of neutral conditions. And this kind of shows you how many hours, when you're designing to the peak condition, you're getting in Colorado. You're running, at your design temperatures, you're roughly 77 hours out of the 8,760 hours a year. less than 1% of the time it's actually running in its full capacity mode. And it's really running in lower capacity much more of the time, 1,600 to 5,000 hours per year. Similarly, in Georgia, same thing. At peak cooling conditions, you're at 155 hours a year, but when you're in that intermediate zone of 78 to 90 degrees, you're 10 times the run hours. So we found that cheating the system a little bit in terms of the peak conditions to favor it for more of the longer operating run times may be favorable when you're trying to make some decisions on sizing of equipment and predominantly on airflow selection of how much air do you put into a room. These are sort of just showing some of the differences between the loads in at the peak design conditions, where that same house is running about a 37,000 BTU heating load, 25,000 BTU cooling load, with the indoor temperatures on the ZERH. When you translate that back to a slightly lower design cooling load and a significantly higher 32-degree, this is -3 outside temperature for heating and 93 for cooling, and then you jump that down to 90 degrees for cooling and bump it up to 32 for heating, you get roughly half the peak load on the design temperature for the heating side, but your cooling load doesn't shift a whole lot, and that's predominantly because in these buildings, the solar gain is what's driving your cooling loads. So these are some of the issues that, as you're selecting airflows, you may want to think about and consider. This is a chart showing kind of the differences between peak heating and peak cooling loads and how they can vary from a CFM perspective as you're going through these buildings. So you can see some rooms, the master bedroom, for example, you kind of make a selection between 35 CFM for heating and 58 CFM for cooling. Well, depending on where that master bedroom is, you may want to favor it a little bit towards the cooling side, or you may want to favor it towards the middle of the two. If it's a north-facing with not a lot of west glass, you probably, you may want to favor that a little bit lower towards the heating side. But if it's a west-facing bedroom, that 58 is probably going to be what you're matching to. So, or the master bathroom, sorry. So we've historically, we don't have necessarily a scientific formula we can give anybody to say this is the right way. What ACA recommends is you pick the highest airflow for the room, and that is what you should design the ductwork and the system for. We found that can be problematic because if you actually add up the heating and cooling CFM, you typically get more CFM than the total CFM that either the heating or cooling will give you. And so we've done a little bit more kind of artistic and balancing of these loads and CFMs to favor them in one direction or the other, back off a little bit on cooling in anticipation that the system will probably be working better at a more intermediate level. So the other challenge there is with multi-speed equipment, if you're designing for that peak airflow, but the system is running predominantly in a lower airflow mode, you're going to be getting much lower velocity and less airflow at lower velocities. And so by slightly undersizing these or designing them a little bit under their design CFM, you can help to get the distribution working better when it's running in that lower stage mode. So we take from there on the load calcs to say once we've designed it, it's really now about where are you putting the air in the room, and how are you making that air move and mix throughout the building. We have found and had very good success with high sidewall supply registers in both heating and cooling climates. interior based. This gives you the opportunity to do a very compact system. But of critical importance here is to make sure that where you're putting the air in the building is outside of the occupied zone. You want to do this predominantly to make sure you're not going to be impacting any drafts. Historically, air was delivered at the perimeter of the building to warm up the bad thermal enclosure that we had and raise the mean radiant temperature of the surfaces to make people, again, feel more comfortable. As we've improved the enclosure, we don't need to do that as much, and now we have the opportunity to run these from either a mid-plane ceiling diffuser perspective or from a high sidewall on the inside. It's important when you're looking at the design of the system is what are you picking the register for? And throw and spread are two kind of important factors to look at. We typically are selecting registers more for throw than for spread at this point. Spread historically was useful as a perimeter floor distribution strategy when you had the register under the window and you were trying to blanket the wall in warm air to raise that temperature and to try to overcome some of the infiltration effects that may be happening at the perimeter. With better buildings, a high sidewall, a longer throw we found is better to help enhance full mixing throughout the building and throughout the room. The other consideration that you need to do in looking at register selection is what is the noise criteria and what is the airspeed that you're trying to achieve in the system. Manual D recommends upwards of 800 or 900 as the top limit for air speeds from a noise perspective, and this shows kind of the difference in the throw when you go from, say, a 400 CFM face velocity or 400 feet per minute as a face velocity for an 8x4 register. If you're using that as a high sidewall, it would only get to about 6.5 feet into the room before it would start to drop. Whereas if you're up at 800 or 900 feet per minute for that register, that will throw air and get it pretty much out 13 to 15 feet, which is where you would expect it to be to hit that exterior wall and start moving down the wall plane. It's also important to recognize that not all registers are created equal. These are some tests we did of manufacturers in our lab here, and looking at the throw characteristic of these versus the airflow rate. And we see, depending on what you go for, you can get throws of 10 feet at 130 CFM, but you could also get throws of 6 feet. So there is a wide variety of performance that these different registers do, and generally our experience has been that the low static pressure, low static drop registers with adjustable vanes are a good selection. We've also had some good experience with the ceiling mounted stamped curved blade diffusers for ceiling applications. And this just shows some of the differences between how you adjust the blades and how far the throw gets in a different with different degrees. This is a 45 degree, having more spread than throw can get you out about 12 feet. But if you really want to push it, if you had a straight blade pointed straight ahead, you could get upwards of 19 feet out of this particular diffuser. All of this information is available from the manufacturers, but not widely used, and I think it's important to do. There's also, and this gets into some fairly esoteric stuff, but you can also take the manufacturer's data and adjust it for the actual conditions of the air that you're moving. And this is all pulled out of the ASHRAE 2009 Handbook of Fundamentals, but it gives you a way to come up with an adjustment factor for a register that you can then put in and come up with different throw characteristics based on the exact number of CFM that you're doing and the exact type of register that you're using. This K factor is actually gives you a way to modify how the diffuser actually works. You can see a zero deflection high sidewall grill has a K factor of 5, whereas a baseboard with a wide spread has a K factor of 1.8. And that's kind of an indicator of how much throw you're getting versus how much spread you're getting. But there are ways that you can utilize this formula to come up and understand exactly how the registers you're using. We found this useful, that the registers generally have been rated at about a 75 feet per minute as the terminal condition of the throw. We would like to know what it is at 50 feet per minute. And so, plus the air flows that they usually test these at are fairly high. We're finding it's not unusual to find 30, 40, 50 CFM coming out of these registers. The end result of all of this starts to get to, we need really tiny registers, and we're not seeing them necessarily available in the residential market. So we have frequently gone to commercial application, commercial diffusers, which unfortunately raises the price of the system, but gives you the performance that you're looking for. The other challenge and important piece to look at is the velocity of air that you're moving. How fast is it going through the duct and coming out of the supply register, and how many CFM do you actually need? And a good duct design here will say, yeah, we've got different lengths, different CFM requirements. We're going to get different diameter ducts, and we're going to get different velocities, but they're all within a range. You might look at this and say, okay, manual D done. This system will work fine. Well, in this particular house with this particular builder that we worked with, this is their actual duct design and layout, and they have said that for that 4-inch diameter 32 CFM, they're going to put a 10 by 4 register in, same as they're going to put in for the 101 CFM. And we asked them, and the builder said, well, the contractor told us we use 4 by 10 registers for floors, and that was it. In reality, you really need to pick these registers according to the airflow to get the throw that you want out of that register, and this is something we've seen. So at that 101 CFM for the 4 by 10 register, you'd get a throw of somewhere in the 8 to 10, maybe 12 foot range. You get about a 7-foot spread. When you go down, we can't even go down to the 32. They don't even have it at have that listed as a CFM requirement for that 4 by 10. But if we almost doubled that airflow, you'd only have 3.5 or 4 feet of throw out of that register. And so probably that register should be up selected to either a 2 by 10 or even something smaller. We still are not getting as much throw as we would like, primarily because that's the function of the 10-inch wide by 2-inch width of that register. Probably a better selection here would be going to an 8 by 4 or even an 8 by 3 or 8 by 2 would probably give you the throw and airflow characteristics that you'd want. And that's going to impact the air speed in the duct and the air speeds, which, again, will go back to influence how the duct system may be designed. So we've looked a lot at airflow, how it works in rooms. We've done this both through physical testing and modeling. And some of the conclusions we're coming to is that as we get cooler air at higher speeds, the air in the room gets good mixing. When we introduce that air at a much higher temperature, which is more typical of a forced air furnace, at a lower airspeed in the high sidewall, this is where you start to get stratification, the red being the hotter, the blue being the cooler. This is a snapshot of a room coming off of setback and could be problematic. So lower air speeds, these 300, 400 feet per minute, it can create stratification problems by virtue of you're dribbling that warm, hot air in, and you're not really engaging the the room air as much as you would if you're putting it in at a much higher speed. This is the same cubic footage of air. You're still introducing, I think in this case, about 50 to 60 CFM of air, but it's just a difference of how fast it's being introduced at that register. So we're really urging builders and HVAC designers to look at increasing the air speed in your systems to maintain a higher supply outlet velocity to help mix the air in the room. These are some other modeling simulations showing the difference between a kind of a standard register and that air, the airstream lines coming in and sort of filming at the top, as opposed to a higher velocity diffuser. This is just basically a 3-inch diameter outlet that enables that air to move much more quickly, hits that back wall, bounces around, moves down. Similarly, in the cooling mode, you see with the standard register, the airflow simply kind of drops out of the register and falls to the ground, mixes a little bit in the room, whereas the high velocity 3-inch diameter diffuser really moves the air and mixes it throughout the course of the room. This is another way to visualize it, and I've got a few CFD animations here to show. This first one is the high velocity jet coming off of cooling or coming off of a heating setback. And again, we're not seeing great mixing because this is a fairly low airflow, about 30 cubic feet. But you see it does engage the air. This is a cross-section through that room showing how that air might move and engage. And the challenge with these high sidewalls is that in the heating mode, the warm air has a tendency to rise. In the cooling mode, they have a tendency to drop. This is comparatively the same room with the same CFM airflow, but coming out of a standard vent. And you can see a much more unified sort of temperature drop in that room as the warm air kind of fills the room from the top and pushes the cold air down without really doing a whole lot of engagement or mixing of the air in the room. This is where we could see stratification problems occur. This is the same room in a cooling mode. We have a high sidewall jet coming out. Blue is cold, red is hot. Again, coming off of a setback at 85 degrees. And the higher velocity jet really does help mix the room. Here you can see the influence of that, of the airflow and the cooler air dropping in the room and really moving and mixing that air around and engaging it to get that temperature much more uniform. This is a shot of the same room, again, with this standard lower velocity airflow coming out. And it's really, it appears to almost be like a water hose trickling cold air into the building, pouring it and filling it up from the floor to the ceiling. Much less mixing, much less engagement in the room air temperatures. And if you think about your thermostat being at mid-level, well, you might meet your thermostat at a certain temperature if that middle line there is where the thermostat is, and the green bubble is what your temperature is supposed to be. Well, this might turn the system off right here, and you've still got a high level of stratification in the building. So something to consider. Finally, we've been finding that bringing the perimeter systems back from the outside walls, doing compact duct systems, you can really minimize the amount of material, minimize the number of registers, and get a much more consistent duct length on every duct, which helps you in the design process to get the right diameter for the length and airflow. These are kind of my last two slides, just showing the impact of the mass of a duct system. If you were to think of this system being one made out of flex duct and duct board, and the other being made out of sheet metal, this first one would be the flex duct and duct board system. When the system kicks on, and these are measured temperatures from February in a building, two side-by-side buildings, so they were identical buildings built identically with two very different duct systems. This is a low-mass, compact duct system in the building. And you see that these are the air temperatures at the supply outlet. And as the system goes on, pretty much all of the air temperatures are very consistent within about a 5-degree range. You've got one that's a little bit lower, but for the most part, you're getting very consistent air delivery temperature out of each of these, and it satisfies the load, turns off, you get some spread, but as the system comes on, all of these air temperatures are very, very consistent. This, in comparison, is the all sheet metal duct system that runs to the perimeter of every room in the house. And you see a much wider spread from 90 degrees up to even 105 degrees as supply outlets. And you look at the room that hottest air is coming out of, it's the nook, which is closest to the thermostat. You look at this, you know, what are these air temperatures that are in the 90s or 95 degree range? Well, it's a bedroom or the master bedroom. So you may be needing to not, this is where air balancing becomes perhaps can be problematic, that if you're simply balancing on an absolute uniform temperature of air coming out of there, you may be providing more air to the spaces that are need it less, and starving air from other rooms that could be using it more, not because the air flow itself is wrong, but the temperature of the air varies as you get the length of runs in these systems. So doing more compact systems, using materials that have a lower mass for heating up or cooling down can be beneficial in the designs of the system. So in conclusion, we're kind of, you know, the equipment is critical to pick the right piece of equipment with for the load that you're calculating and looking at the CFM, but having the ducts really be designed and installed for the design is the other issue that we've seen. Make sure it's done right. And looking at higher velocities in the duct systems, typically we've seen that the computerized software tools generally are looking at 300, 400, maybe 500 feet per minute as velocities in the systems. We have historically been designing anywhere from 500 to 900 feet per minute to get that mixing and throw at the register. It may require a slightly different methodology called variable friction method. I'm not sure that a lot of manufacturers or the software companies are moving in that direction, but there are ways you can adjust that if you look at the appendices in Manual D. We also want to make sure that the supply outlets are really picked. It's critical to understand what the performance characteristics of the supplies are. All of the manufacturers have performance data that can be used. The frustrating part we found, unfortunately, is that many of them are not creating diffusers and outlets that are small enough for the airflows that we're looking at. And we've been studying, as I said, some of these smaller diameter, higher velocity systems as an alternative to that. So the end result is we're working with product manufacturers looking at how do we maintain a higher air velocity with lower supply air temperatures and heating to maintain longer run times, get better mixing in the space. A workaround for this now is to have an air cycler or some other kind of fan-only operational mode that runs periodically to help mix the air in the building. And these can be pretty effective, but and when integrated with ventilation may not give you much of an energy penalty, but could be problematic. You know, they may run slightly higher energy costs than fan energy if you're not doing them with an integrated ventilation strategy. So that's about it. Thank you to all of you and our project partners that we've been working for probably 12, 14 years on this with. Cardinal Glass helped us out with some test houses that they had running. Carrier Corporation has been a long-time sponsor, and National Renewable Energy Lab has supported us with some of the CFD work and modeling. So with that, I'm ready to take any questions that might be coming in. Jamie?
Okay, thanks, Duncan. I guess just a quick personal observation here is that put out a lot of really good information, and if a builder and their HVAC trade partner were more still using traditional methods, maybe more up to speed on right sizing at this point, but this concept of totally reevaluating terminal location and air velocities and going for this mixing, and you're showing CFD-based simulations, it's sort of a lot to sort of grasp all at once. You showed some resources earlier on. Is there sort of a first stop that you'd recommend people look at to sort of be able to review this in writing and see what the recommended practices are for terminal location, ideal exit velocities out of the terminals, and so on?
Yeah, the guides that I mentioned earlier, which are on the Building America Publications website, if you search for Building America Publications, and there are 3 strategy guidelines that we've done for load calcs, equipment selection, and compact duct systems and supply outlet locations. Those would be useful resources, and we can do there are hot links. There are links in this presentation that can get them there, and I would say that would be a place to start. We're working right now to try to work with ACA and some others to update Manual T to actually have more of this type of information in it, so that this is embedded within the sort of industry standard manuals, and also discussing with the software manufacturers whether there's some other ways to be able to do duct designs with a higher velocity duct strategy, where you actually pick the velocity of the air in the duct as opposed to picking the equivalent of the friction rate for the duct systems. So those are in the works, but not currently on the street per se. And
the Manual D duct design software that's typically used in the residential marketplace, does it have any accounting for mixing within a given zone, or is it simply looking to see that enough CFM is provided?
It primarily is driven by the CFM requirement in the room. It allows you to see what the velocity is, but I'm just trying to find, yeah. So this is a printout of one of the software packages, and it does tell you what the velocity is in the ductwork. And if you go in and manipulate the diameter of the duct, it will increase the velocity of the duct. It'll also increase the static pressure. So it's kind of a balancing act that you need to look at. But it does not typically say that you should have, when you sort of work on the defaults, you're going to generally get duct systems that are running velocity somewhere between 300 and 500 feet per minute. And we're finding that it's challenging to get the throw and mixing that you need out of the supply outlet at those lower velocities. So it may be something that needs to be looked at and manipulated in Manual D as you're doing that work, to kind of balance between the getting a higher velocity and the static pressure, which again is a challenge that if you have longer duct systems with more static pressure, you may not have enough blower fan energy to actually make it work, or oomph, I guess, to say, the fan pressure. However, by bringing the duct work down into a compact and shorter system, you have less equivalent length, less friction in the ducts, so you can afford to use a little more of that static pressure for your velocities.
Okay, good, thank you. Let me open up some of the questions that came in from our group. One that came in somewhat earlier, it's about window U factors, and it states that from a comfort perspective, if we move from a window with a U factor of around 0.33 down to a window with a U factor of 0.25, from a comfort perspective or standpoint, will the occupant really be able to notice the difference from a comfort standpoint in the thermal performance of the window?
My suspicion, we have not measured that, but my suspicion is no. A lot of the measurements we've done with mean radiant temperature versus air temperature have been done with pretty good, I mean, not triple glazed windows necessarily, but good double glazed low E windows in the 0.3 to 0.33 U factor range. I think a lot of it has to do with the low E coating that helps reflect the radiant energy back off of the surfaces. So the U value is not the entire story on that. But I don't know that you will get an appreciable difference in comfort from the mean radiant temperature perspective with significantly lower U values. I think it's more of an energy play that windows are still the weakest link in the building, and the better you can get the window, the less energy you're going to be losing there.
Okay. Here's another one. What about adding a cooling system to a house that's already built? Is there any particular data available? I have a hunch that they're probably alluding to a sort of retrofit high-velocity cooling system application here.
Yep. Well, I think retrofitting cooling can go any number of ways. We've been exploring these small diameter high-velocity systems recently, and are finding that there are some more efficient options out there with variable speed equipment that could be a solution there. We've also been seeing a lot more prevalence of the mini split ductless or ducted heat pump units, and those are fairly high efficiency. And what we found in buildings that have a pretty good thermal enclosure, similar to what the ZERH requirements are, if you have a mini split head in one large open space, you probably are going to get pretty uniform cooling or heating in that space with that device. There may be some localized drafts right under it based on where it's sitting and how its vanes are operating. We haven't seen really a lot of success with a single point mini split in one sort of a common corridor or hallway. On a second floor, for example, with numbers of bedrooms working off of that. We just don't see enough airflow going through the open doors to be able to really maintain uniformity comfort. So on something like that, we probably recommend looking at a small ducted system. But there are very small pieces of equipment available, and as long as you're not using a whole lot of duct work with them, they should be able to maintain comfort in those types of rooms. So there are a few different options: the high velocity, small diameter systems, or these ducted mini splits, ducted and or ductless mini splits.
Okay. Let's move on to the next. So this is sort of a question / comment, sort of asserting that perimeter duct systems can still be a very viable option. Let me kind of summarize here. So if we have a properly insulated and sized duct system coupled with properly sized equipment that runs more rather than less, perimeter systems can be effective and kind of cover a multitude of issues we might get if we don't properly locate the registers. Sort of a comment.
Yeah, no, well, absolutely. I agree 100%. I'm not saying that perimeter systems are bad, but what we're finding in these lower load homes is that we don't need, the historic reason for putting the system at the perimeter was to help wash the walls and really maintain more comfort in the heating modes. And these compact systems can work equally well in both heating and cooling climates as long as the registers have been selected appropriately. And the other advantage that we really are seeing with the high sidewall supply outlets is we have yet to find anybody who's put a couch against a high sidewall supply outlet. But I would challenge anyone to walk through any new construction development of model homes and look at the great room, kitchen, living room, dining area. You're probably going to find, at least if they've done perimeter supplies, at least one, if not multiple outlets blocked by couches, up in the bedrooms being blocked by furniture or bookshelves or bureaus, those types of things. And those can, again, lead to localized discomfort for the occupants in a specific room. And it's kind of hard to tell your occupant, well, you just furnished the room wrong, right? By putting a high sidewall in, you basically have given them there's not much of an option for them to cover or block that device. But I agree, perimeter systems do work well, and they do maintain comfort. There are some challenges with them. The other downside is you've got more material associated with it and longer duct runs. So in trying to increase the velocity of the ducts, you're paying a penalty for the velocity by increasing the static pressure in those ducts, and having shorter duct runs helps to neutralize that increased static pressure associated with higher velocities.
Just an add-on to that, Duncan, you mentioned that with the high sidewall registers, product availability is an issue. Is it even more of an issue to get high throw floor diffusers?
Probably equally challenging, because ultimately your CFM is what's driving the size, and the throw is not a whole lot different. You need a slightly higher throw for a high sidewall than you do for a floor register typically, but not a whole lot. And many of the floor registers are really the adjustable vane or higher performance ones are not as appropriate for floor registers, so that may be another challenge. It's interesting to note that when in some of the work that the University of Illinois did in the early 1900s to early to mid 1900s, their conclusion was that a high sidewall was probably the best option for both heating and cooling, with the floor perimeter being a close second. So they were even finding in moderately insulated buildings in the early 1900s that there wasn't a whole lot of difference between these high sidewalls and perimeter distribution. And a lot of it had to do with preference of where you could get ducts and how much basement you did or didn't have.
Okay. Let's wrap up with one more before we turn it back over to Lindsay here. So this is a little bit more of a comment. We can see what Duncan's reaction might be. It states that I added 90% shade screens on the exterior of the west side windows with 0.35U windows. From a comfort standpoint and solar heat gain perspective, this made a huge difference in the Central Valley of California. So sort of
absolutely. And that touches on something that I didn't really go into, but we've measured, is that the other challenge with space conditioning systems is the localized discomfort you can get by the solar gains. The solar gains and cooling are really going to be what drives your load. And more to the point, if you are not really mixing the air throughout the building, then you can have localized discomfort in a bedroom with a door closed in the west side, or we've even seen on the east side of the building in the morning, that if that temperature that's going into that room is not being communicated to the thermostat and that the space conditioning system isn't responding to that, then you can seriously see very significant temperature swings. We've seen in Pittsburgh, an unoccupied lab house we've had here, anywhere from 6 to 8 degree temperature differences, and these are on moderately warm or moderately cool sunny days. These are not peak load conditions by any means. So one strategy that we also have been exploring and we'd recommend people look at is there a way to do multiple temperature sensors throughout the house that communicate to the thermostat that give a better average temperature of all the spaces in the building, not to zone the building, but just to control the fan operation of the building, where you may have some western rooms that are heavily glazed that could overheat relative to where the thermostat is actually located in the building, and having a fan operation that circulates air through the building in some modes, and then when heating or cooling is needed, the thermostat will kick on for that. But yes, absolutely, anything you can do for, especially in cooling climates, to provide very low solar heat gain on those west faces are going to be going to enhance comfort significantly. So.
Okay. Lindsay, you want to shift it back to your slide just to show a few of those other resources before we wrap it up?
Absolutely. Let's see here.
Okay, so while Lindsay queues up the slide, it just shows a few more of the resources. Duncan mentioned the Building America Publications library, which is certainly a great place to go to dig deeper into some of these topics and look at some of the resources he mentioned. In terms of the DOE Zero Energy Ready program, other events, the website's right there, buildings.energy.gov/zero, and that's sort of the one-stop shop for all kinds of program information, including the events like these webinars. You can see the upcoming schedule of the in-person trainings that cover sort of soup to nuts, the business case, the value proposition, and sort of a technical overview of the DOE Zero Energy Ready program. And then you can also see about upcoming conference presentations. In terms of locating builder partners and verifier partners, there's a locator tool. You can see the actual program specs for how DOE is defining and qualifying homes to be zero energy ready. And then lastly, as we mentioned right up front, these webinars are being recorded, so you can take a look at them or point them to colleagues so they can take a look at them on their own time and schedule. And then lastly, that final link there is the Building America Solutions Center. You can get to many of the publications that Duncan mentioned through that vehicle as well. Building America is DOE's leading residential research program, which has been underway since the 90s, and it's collected a vast amount of really good technical information on how building systems work, how they need to be integrated. And in the last couple of years, DOE has taken a huge leap forward in trying to make all that information much more navigable and easily found for builder partners and trade contractor partners and the like. So it's much more user-friendly now. You can navigate it through a number of different taxonomies to drill down and find information, whether it be a CAD detail, right versus wrong photos, model specifications, code language, many different layers of guidance arranged by building system or by the checklist you might be using for the Energy Star program. So that's worth noting, that site as well, the Building America Solutions Center. And with that, here's our contact info, the website, the email, and please feel free to follow up with any of us. But on behalf of DOE and Lindsay and certainly Duncan Prahl, Vibicus, thanks for joining us today. Enjoy the rest of your Tuesday.